Okay, so continuing our conversation about circumparabolas of Poncelet triangle families. Let's take now the case of the so before we're actually looking at the isotomic image of lines tangent to the Steiner circumellipse, let's now take another method to construct a circumparabola of a triangle. You actually draw its circumcircle, and then you pick a tangent to the circumcircle, and now you consider the isogonal, not isotomic, the isogonal image of a line tangent to the circumcircle with respect to a given triangle. That's also going to produce a circumparabola. So you can actually scan or traverse all possible circumparabolas to a triangle by either running through the tangents to the Steiner and computing their isotomic images, or running tangents around the circumcircle and computing their isogonal images. So now I'm actually looking at a Poncelet family inscribed in a circumcircle. Let's try to exploit that, right? So what do I have now? I have a P1, P2, P3, which I can jog in a Ponceletian way, and I can observe its circumparabolas modulo their passage through infinity, which Mathematica is not too crazy about, right? And I'm showing for each circumparabola here, each of these red circumparabolas, the focus, the vertex, and let's call this the intersection of the foot, or the intersection of the axis with the directrix. Here's the directrix. Okay, so one thing we can ask is if the focal length of this thing is constant as we jog Poncelet. That's not so germane, but you can see here that the focal length is not constant, right? You can see that F and V are pretty close here, and they're not close if you go over here. So you can also say, okay, what's happening to the geometry of this parabola if I play around with my tangent? Does it conserve anything? Is the focal length being conserved? Does it look like it could be? It doesn't look like it, right? You can see that it's pretty stretchy here, and it gets a bit smaller over here, right? So that focal length is not getting conserved. But that's actually not germane to what I actually want to show you guys. What I want to show you guys here is, first of all, we've lost that previous property that this family of circumparabolas was tangent to a particular line. And in fact, I don't know if the envelope swept by the circumparabolas as I jog Poncelet is doing anything interesting. So I have to explore that. Okay, so I can explore the envelope of these parabolas as I jog Poncelet, or I can explore the envelope of these parabolas as I jog my tangent. Is either one of these two phenomena doing anything interesting? Okay, you can see here that the parabola is going to be shooting to infinity, right? So whatever locus of F and V as I play around with my tangent, these are not going to be compact curves. They're going to shoot off to infinity, but that's fine. By the same token, if I jog Poncelet, you can see here that since the parabola does go through infinity, okay, and I think it goes to infinity when one of these sides here becomes parallel to my tangent, okay, I'm not going to have a compact locus for F and V either. But let's go ahead and draw those loci. So I'm going to draw the locus of F, the locus of the vertex, and the locus of that foot of the directrix, so we can just take a look at what's happening as I jog Poncelet. Very cool. These don't look like very low degree curves. Back in the homothetic case, I told you guys that the locus of the focus was at least of degree 9. I don't know what this locus is. I don't know the properties of this locus. And by the way, what's the locus of F, which I haven't implemented yet, as I vary my tangent? I don't know. Okay, it's going to be something interesting. All right, now I actually want to get to the main result here. Let's go ahead and now switch to a different Poncelet family, also inscribed in a circle, but let's say more primitive. We're going to call this, or we're going to switch to something called the Bicentric family. And let's just recap what the Bicentric family keeps coming back on my videos, right? It's a family of triangles, also known as Chapple's Porism, or the Poristic family, with fixed circumcircle and fixed incircle. So this family has been studied for at least 200, if not 300 years. Okay, now I'm going to do this new twist with it, in that I'm going to place a tangent somewhere on the circumcircle, and I'm going to compute its isogonal image. And I want to know what happens to the foci, to the locus of the focus. So let's go ahead and draw, first of all, the family of circumparabolas so that we make sure that everything is going on as we expect. So there is a family of circumparabolas. Once I pick a particular tangent, of course I can change which tangent I'm going to pick, and then I'm going to jog this family in a different way. Okay, but the phenomenon that one observes here is the following. Pick a tangent to the circumcircle, and I'll jog the family, the Poncelet family. Jog the Poncelet family. What is the focus doing? Ooh. Okay, let me just go back to something like this. Okay, and yeah, let me just yes. Okay, I had to play a little bit with the parameters here so that Mathematica doesn't explode, but I think I'm back to normal now. If you pick some generic tangent to the circumcircle and you jog the Poncelet family, a miracle happens. The focus moves along a straight line. Now the specific straight line depends on which tangent you pick. So let's go ahead and pick a different tangent. I'm going to jog this guy very carefully here so I don't break Mathematica. Well, I've jogged the tangent in the wrong direction. Let's go back to where we were before. Hang on. So I'm over here. You can see that as I jog my tangent, and I can get these explosions here. Let's make sure that these explosions don't happen. Let's see on one end I need to. Okay, so that's not the one that I have to change. I have to change this one here. These are the limits of locus computation, if you will. So I change my tangent, and I can now play with the tangent in this region, so you guys can see more or less in a continuous way how the locus of the focus remains a straight line. This is very surprising, given that, as we saw in the circumcircle family, this locus was a triad of high degree curves. So this appears to be the one circumscribed Poncelet family where the locus of the focus collapses to a linear curve, to a line. Now, can I say the same thing about the locus of the vertex, for example? It looks straight, but it's not straight, right? You can see here that it already has some curvature, and it deviates, so if I scale this up, it becomes more clear. This is not a straight line. The locus of the vertex is not a straight line as I jog Poncelet. And neither is the locus of that foot of the directrix as I jog Poncelet. So the observation here, which is rather unexpected, I actually wasn't expecting for the locus of the focus to be a simple thing anywhere, given that it's a degree of 9 in the homothetic and it's a high degree on the circumcircle, and you're going to see that it's a high degree in another family called Brocard. I wasn't expecting for this to happen. So I have this other example here called the Brocard family, which is also inscribed in a circle, and now it circumscribes an ellipse known as the Brocard inellipse. So it's also a non-concentric pair, but the difference from this, from the bicentric, is the fact that the caustic now is elliptic, right? So if you go back to the bicentric, the caustic is a circle, and in the Brocard, the caustic is this Brocard inellipse. The foci of these inellipses are the fixed Brocard points of the family, but that's not germane. But look at what happens in this family. Locus of the focus is not straight. See that this is a non-straight curve, like a sinusoidally moving curve, right? As are the loci of the vertex, the magenta curve, and the locus of that center point of the directrix. Okay, so the Hocus Pocus phenomenon is that the focus locus of my bicentrics is a straight line. I'll see you on the next video.